أهلا وسهلا بالجميع. محاضرة اليوم بعنوان Non-Uniform Robust Quantization. This is an outline of today's lecture. In this lecture, we define the non-uniform robust quantizer, define the mu-law compressor and expander characteristics, show the improvement in signal to quantization noise ratio of non-uniform quantization over uniform quantization, present a number of illustrative examples. First, let us review some of the basic definitions and concepts related to quantization which we covered in the previous lecture. We start with the definition of quantization. Quantization is defined as the process of converting the continuous amplitude samples x of kts of a message signal into a discrete amplitude x cap of kts taken from a finite and countable set of possible values x cap. This is a representation of the quantizer. The input to the quantizer belongs to a set of continuous values discrete in time. The output of the quantizer belongs to a set of discrete amplitude discrete time values. The dynamic range of the quantizer is the range of values for which the quantizer is designed. The quantizer is designed to operate between a range of values extending between x minimum and x maximum. This is what is called the dynamic range of the quantizer. This range of values is partitioned into L non-overlapping intervals such that if x of kts, that is the sample, belongs to some region Ri, the quantizer output will be a level xi cap, which belongs to this set x1 cap, x2 cap, up to xl cap. This is the dynamic region of the quantizer extending between x minimum and x maximum. This region is partitioned into L non-overlapping intervals. This is one interval between x0 to x1, another interval between x1 to x2, and so on. These intervals are non-overlapping. The quantizer output is called a representation or reconstruction level. These are representation or reconstruction levels. The boundary points separating adjacent regions are called decision or threshold levels. x0 is a threshold, x1 is a threshold, x2 is a threshold, and so on. x1 cap is a representation level, x2 cap is a representation level, and so on. So the whole idea, if the continuous sample x of kts belongs to this set of values between x0 to x1, then the output of the quantizer will be x1 cap. So the whole set of values will be mapped into one value, into one level, which we call x1 cap. If the continuous set of values x of kts belongs to this interval between x1 and x2, the output of the quantizer will be x2 cap. So regardless of the actual value of the sample, the output is the same, and that will be x2 cap. The spacing between representation levels is called the step size delta. This separation between x1 cap to x2 cap, this separation is called the step size delta. For a uniform quantizer, the step size is also the separation between the thresholds. The step size delta in general equals the maximum value minus the minimum value divided by the number of representation levels or the number of intervals. This is the step size delta, and also this is the step size delta. A quantizer is called uniform when the L regions are of equal length and the spacing between representation levels is uniform and equals to delta, where delta equal x max minus x min over L. So in the special case, when the quantizer is uniform, the spacing between the decision or thresholds is called delta, and it also equals the spacing between the representation levels. That is x2 cap minus x1 cap equal delta. x2 minus x1 is also equal to delta. Drawbacks of the uniform quantizer. The uniform quantizer is easy to build. However, it's not optimal when the input signal is weak most of the time. Here, the signal does not use the entire set of available quantization levels. Maximum signal to quantization noise ratio is achieved when the signal strength matches the dynamic range of the quantizer. Demonstration: let the sinusoidal signal x of t be applied to a uniform quantizer with a dynamic range minus a to a. We have seen in previous lectures that the signal to quantization noise ratio depends on the signal power. As the signal power decreases, the signal to quantization noise ratio decreases, since the quantization noise is constant. The quantization noise depends on the quantizer itself. It depends on the step size of the quantizer. Also, in the previous lecture, we derived this relationship for the quantization noise, or the average quantization noise, which is the step size square divided by 12. The quantization noise is constant and is independent of the signal power. It depends on the hardware, on the design specifications of the quantizer. As the signal power decreases, the signal to quantization noise ratio decreases, meaning that there is a deterioration in the signal to quantization noise ratio. So this is one disadvantage of the uniform quantizer. Let us consider this illustration. Let x of t equal a cosine 2 pi f1 t. The signal to quantization noise ratio for this signal is 3 over 2 L square. If the input is a over 2 cosine 2 pi f2 t, then the signal to quantization noise ratio is 12 over 32 L square, and this is 1/4 the signal to quantization noise ratio corresponding to the first case. Let further x of t be a over 4 cosine 2 pi f3 t, then the signal to quantization noise ratio equal 4 over 32 L square, which is 1 over 16 signal to noise ratio corresponding to the first part. Now let us assume this scenario. That is, we apply this signal 10% of the time, apply this signal 20% of the time, and apply this weakest signal 70% of the time. This means that 10% of the time, the signal to quantization noise ratio is high, it's the highest. 20% of the time, the signal to quantization noise ratio assumes this level, and 70% of the time, the signal to quantization noise ratio is the smallest and takes on this value. This is the smallest among all values of the signal to quantization noise ratio. In the first case, this is the best scenario. Here, as we can see, the signal, our signal x of t, spans the entire range of values for the quantizer. The signal x of t matches the dynamic range of the quantizer, and in this case, we attain the highest value of the signal to quantization noise ratio. As the signal power decreases, the signal to quantization noise ratio decreases. In this case, some of the levels on the extreme sides will not be utilized, meaning that only these levels around the origin will be occupied or will be utilized. In fact, we can compute the average signal to quantization noise ratio as a statistical average. So the expected value or the mean value of the signal to quantization noise ratio is this probability of occurrence times the signal to quantization noise ratio plus this probability times this value plus this probability times this value. So we compute the average signal to quantization noise ratio as 0.1 times signal to quantization noise ratio 1 plus 0.2 times signal to quantization noise ratio 1 divided by 4 plus 0.7 signal to quantization noise ratio divided by 16, and after calculation we get 0.19375 signal to quantization noise ratio 1. As we can see, the average value of the signal to quantization noise ratio is well below the highest value, which is this one. It's only less than 20% of the maximum value. So the average signal to quantization noise ratio is closer to that of the smallest value. It's very close to this value because this value has the highest probability of occurrence. The overall performance, of course, is not satisfactory. We recall this example from the previous lecture. That is, a signal matches the dynamic range of the uniform quantizer. X of t equal 10 cosine 2 pi 10 t is applied to a uniform quantizer with a dynamic range between -10 and 10, and we assume that this is an 8-level uniform quantizer. The step size for this quantizer is this dynamic range divided by the number of levels, so that will be 20 divided by 8, and the step size is 2.5. This is a plot of the message signal. This is the original signal, and this signal is sampled at a sampling rate of 100 samples per second. Now the Nyquist rate for the message signal is 20 Hertz, which is twice the message bandwidth. So we are sampling at a rate which is much higher than the Nyquist rate. This is our sampled signal. Next, we apply the signal to the uniform quantizer. This is the quantized signal. The quantized signal is passed through an ideal low-pass filter with a bandwidth of 50 Hz, which is 1/2 the sampling frequency. The output of the low-pass filter is this signal. This is the recovered signal. As we can see, there is a high level of similarity between the recovered signal and the original message signal. The reason is that our signal matches the quantizer. The signal extends between -10 volts to 10 volts, and the quantizer specifications also, or the quantizer dynamic range also extends between -10 and 10. So the range of values for the signal matches the quantizer dynamic range. In this case, these levels, these quantized levels, actually take on any one of all the 8 possible quantization levels. So all of them, all the quantization levels will be utilized by the quantizer. So we have a high signal to quantization noise ratio. We repeat the same example. However, we reduce the amplitude of the signal to 1. Our signal now becomes 1 cosine 2 pi 10t, the same quantizer with the same dynamic range and the same number of levels. A dynamic range between -10 and 10, and the number of levels is 8 levels, so the step size again is 20 over 8 equal 2.5. Now this is our signal, varies between -1 and 1. We maintain the same sampling frequency, which is 100 samples per second. Again, this sampling frequency is higher than the Nyquist rate, so this is the sample signal. The sample signal is applied to the uniform quantizer. As we can see, the output of the quantizer assumes only one of two values, either delta over 2 or minus delta over 2, which is 1.25 or minus 1.25. We observe that the signal actually varies within this interval and this interval. Half the time the signal assumes values between 0 and 1, and 50% of the time takes on values between 0 and -1. Whenever the signal is positive, it takes only one value, which is 1.25. When the signal is negative, it takes on the value minus 1.25, which means that this level, minus 8.75, minus 6.25, minus 3.75, 3.75, 6.25, and 8.75, these levels are never utilized by this quantizer. The level of quantization noise is high. If we pass the signal, this quantized signal, through the low-pass filter, a low-pass filter with a bandwidth of 50 Hertz, what we obtain is this signal. This is the recovered signal. As we can see, the degree of similarity between the recovered signal and the original signal is very, very low, meaning that the level of distortion is very high. The uniform quantizer is not optimal when we apply weak signals, as in this case. When we apply a strong signal to the uniform quantizer, we get a high signal to quantization noise ratio. When we apply a weak signal, we obtain a smaller signal to quantization noise ratio. The non-uniform quantization, which is the subject of this lecture, will ensure an almost constant signal to quantization noise ratio for strong as well as weak signal components. There are two main advantages of the non-uniform quantizer. The first, the signal to quantization noise ratio is higher than that of the uniform quantizer. As we shall see, the average signal to quantization noise ratio of the non-uniform quantizer is higher than that corresponding to the uniform quantizer, meaning that there is an overall improvement in the signal to quantization noise ratio. And second, the signal to quantization noise ratio is almost the same for all signal components. That is, we shall not see a scenario like this where the signal to quantization noise ratio varies over a wide range of values. For the non-uniform quantization, the signal to quantization noise ratio is almost the same for strong as well as weak signal components. That is, it provides some sort of uniformity among signal component in terms of signal to quantization noise ratio. Uniform and non-uniform robust quantization. In practical applications, especially speech signals Small signal amplitudes occur more often than large signal amplitudes. This means that for the same signal, small amplitudes will be subject to distortion more than large amplitudes. That is, large amounts of distortion have a higher probability of occurrence. F of x is a typical probability density function for the speech signal. As we can see, smaller amplitudes have higher probability of occurrence. However, these high amplitudes will have smaller amount of distortion. These smaller amplitudes will have a higher level of distortion. This means that the overall effect will be a higher degree of distortion. The non-uniform robust quantizer, which employs the mu law, can provide a signal to quantization noise ratio that is somewhat constant and independent of the signal strength, provide a signal to quantization noise ratio that is independent of the probability distribution of the sample signal. That is, we can remedy this situation where smaller amplitudes will suffer higher amount of distortion by employing a non-uniform type of quantization. There are certain types of quantizers which require knowledge of the probability density function in order to minimize the mean square error. But obtaining the probability density function and designing the quantizer which matches this density function is a difficult task. It's better if we can find a quantizer, an optimal quantizer, which does not require knowledge of the exact shape of the probability density function, and also provide constant signal to quantization noise ratio for strong as well as weak signal values. This example actually demonstrates the idea. Small amplitudes have higher probability of occurrence. Small amplitudes have small signal to quantization noise ratio. High amplitudes occur with lower probability. High amplitudes have high signal to quantization noise ratio. The average value of the signal to quantization noise ratio is much smaller than the maximum value. Non-uniform quantization. We will use a type of non-uniform quantizers called companding that does not require knowledge of the probability density function of the signal to be quantized and yields an almost uniform signal to quantization noise ratio over a wide range of signal variations. The process of pre-distorting the signal at the transmitter is known as signal compression. At the receiver, this process is reversed to remove distortion and is known as expansion. The two operations together are typically referred to as companding or compansion. The compressor is a nonlinear operation that amplifies weak signal values more than it amplifies large signal values, thus stretching the signal over more representation levels. This will enhance weak signal levels and improve their signal to quantization noise ratio. Large signal levels will also suffer from distortion, but the overall effect on the signal is an improvement in signal to quantization noise ratio. Since the probability of smaller amplitudes is higher than the larger amplitudes, the overall result is an improvement. In North America, the mu law companding uses a constant mu equal to 0.55. This is the compressor characteristic. Y, that's the output of the compressor. Y equal Y max ln 1 plus mu, which is 255. X is the input to the compressor. X max is the maximum value divided by ln 1 plus mu, and this function is an odd function in the input variable x. Let us check some values. If the input to this compressor is a sample with amplitude 0.01, upon substituting and solving, assuming y maximum equal 4 and x maximum equal 4, the output is 0.3557. A sample with amplitude 0.01 is being amplified almost 36 times. If x is 1, the out is 3, which is 3 times the input. And if x is 4, the output is also 4. So we have a ratio of 1, which means that the compressor actually amplifies all input values. But the level of amplification varies depending on the value of the signal. Smaller amplitudes are amplified to a higher degree than larger amplitudes. The output of this compressor is applied to the uniform quantizer. The output of the uniform quantizer will be any one of these values. These are the possible outputs of the uniform quantizer. At the receiving side, we employ a characteristic which is the inverse of the characteristic that is used at the transmitter. The characteristic at the receiver is y prime divided by y prime maximum equal exponential. We solve the inverse equation. So we have exponential x prime over x prime maximum ln 1 plus mu minus 1 divided by mu, and we have also a signum function of x prime. This is the input at the receiving side, x prime, and the output is y prime. X prime, the input at the receiver, as we have said, is any one of these output levels of the uniform quantizer. The compressor is a nonlinear operation that amplifies weak signal values more than it amplifies large signal values. This is how small signal amplitudes are being amplified, thus stretching the signal over more representation levels. When the input signal is amplified, this means that there is a higher probability that these high levels will be utilized. If the signal is a small one and we do not use this nonlinear characteristic, then the signal will be confined to these two levels. However, if we employ this nonlinear characteristic, we increase the probability that these levels will also be utilized and therefore reduce the quantization error. Companding is performed as follows. Compress the signal using the mu law. The output is approximately uniformly distributed. In this diagram, we show the whole operation of transmitting a signal. This is the analog signal x of t. X of t is sampled at a rate greater than the Nyquist rate. This is a continuous time, continuous amplitude signal. The output of the sampler is the discrete time continuous amplitude samples. These samples are applied to the compressor. The output of the compressor is applied to the uniform quantizer, and uniform quantizer output is assigned certain binary digits depending on the encoding scheme which we employ. Then it's modulated and transmitted over the channel. Then the output is decoded and then applied to a reconstruction filter to recover the sample value which was transmitted, and then there is this inverse characteristic at the receiver which is the expander. That's the output of this operation. Compress the signal using the mu law. The output is approximately uniformly distributed. Apply the compressed sample to the uniform quantizer. Transmit the quantized sample to the receiver. This is the compressed signal. It undergoes many operations. Apply the received sample to the expander. This is the expander. The output is the desired signal value. Let us take this example. A sample of magnitude 0.01 is applied to a 3-bit uniform quantizer with a dynamic range between -4 and 4. Find the quantizer output, the quantization error, and the value of the sample at the receiving site. So we have a sample value 0.01 applied to a uniform quantizer. This is the uniform quantizer. This is the 8-level uniform quantizer. We subdivide the range of values between -4 and 4 into 8 levels, and so the step size for this example is 1. The representation values are -3.5, -2.5, -1.5, -0.5, 0.5, 1.5, 2.5, and 3.5. The sample 0.01 falls in this segment. Therefore, the output of the uniform quantizer is 0.5. So this means that the absolute value of the error, which is the difference between the input and the output, is 0.49. Now 0.49 relative to the sample value 0.01 means that the amount of error is 49 times the sample value. That is, this sample has been amplified by 50 times. The original sample is 0.01. The actual value which will be reproduced at the receiver is 0.5. So 0.5 is 50 times the sample value. So this is how we can actually assess the amount of distortion. The percentage of error is 0.5 minus 0.01. This is the error divided by the original sample value, which is 0.01 times 100%, meaning 4,900%. This is the amount of distortion as compared to the actual sample value. So the error is 49 times the sample value, or the sample value itself has been amplified by 50 times. If the sample is applied to the quantizer that employs companding, find the value of the received signal and the quantization error. We need to compare the error and the percentage error when the sample is applied to the companding system. The non-uniform quantization, when x equals 0.01 is applied to the mu law, the output y equal y max ln 1 plus mu x over x max ln 1 plus mu equal 4 ln 1 plus 255 times 0.01 divided by 4 divided by ln 1 plus 255 equals 0.3557. The 0.3557 is applied to the uniform quantizer, and therefore the output of the quantizer is 0.5. The 0.5 volts is encoded as 100 and transmitted. We assume that no transmission error occurs. At the receiver, what is received is the 0.5 volts, this value. The 0.5 volts is applied to the expander, which is the inverse of the mu law characteristic, and so y prime, this is the output of the expander, exponential 0.5 by 4 ln 1 plus 255 minus 1 divided by 255. This is 0.5. This is the value that is applied to the expander. The output is 0.01568. So the received sample now is 0.01568. So the error is the input minus the output equals 0.01 minus 0.0157, which equals 0.0057. We need to compare this value with the previous error, which is 0.49. Also, we compute and compare the relative error, which is 57%, with the percentage error with the uniform quantizer, which is 4,900%. This figure demonstrates the whole operation. 0.01, this is the input sample. It's applied at the transmitting side to the compressor, and the compressor yields an output of 0.3557. The output is applied to the uniform quantizer, and this is the level assumed by the uniform quantizer, which is 0.5. This 0.5 is transmitted and is applied to the expander at the receiving side. We apply it to this inverse characteristic, and what we obtain is 0.01568. So this is the characteristic at the transmitting side. This is the compressor. The output is 0.3557. The inverse characteristic, the expander at the receiving side, we have 0.01568. We can clearly see the improvement in the signal to quantization noise ratio. So in this example, we applied a sample of 0.01. The compressor output is 0.3557. The quantizer output is 0.5. The 0.5 is given the binary representation 100, and then it's being modulated, transmitted, and demodulated. At the receiving side, assuming no transmission error, we receive the 100, and so the reconstruction filter will reproduce the sample value of 0.5. Now this 0.5 is applied to the expander, and the output of the expander is 0.01568. With non-uniform quantization, this sample value of 0.01 is reproduced as 0.01568. If we have not employed the compressor and the expander, then the 0.01 sample will produce a 0.5 volts. This figure shows a weak and a strong signal applied to a uniform and a non-uniform quantizer. As we can see, the non-uniform quantizer represents both signals quite adequately. This part, we have the uniform quantizer, and on this side we have the non-uniform quantizer. If a strong signal is applied to the uniform quantizer, the output of the uniform quantizer will be a good representation of the signal, and the amount of distortion is low. The signal to quantization noise ratio will be high. The same if the strong signal is applied to the non-uniform quantizer. The output of the non-uniform quantizer will again be a good representation of the signal. Also, the performance will be adequately high. If a weak signal is applied to the uniform quantizer, the signal is poorly represented and the amount of distortion is high. So the signal to quantization noise ratio is low. If the same weak signal is applied to the non-uniform quantizer, the signal will be represented in a good way by the non-uniform quantizer, and the quantization noise will be low, meaning that the signal to quantization noise ratio will be high. Or this is a comparison between the performance of the uniform and the non-uniform quantization for both weak and strong signals. هاي نهاية المحاضرة، إلى اللقاء.